to Kinetics, our fourth out of 6 AP chemistry units. So congratulations for making it over halfway through. We're going to start off by bridging our last unit to this unit. Thermodynamics and kinetics together give you a really powerful and very complete understanding of a chemical reaction. If thermodynamics explains the why of a reaction, why a reaction happens, why reactants turn into products, then kinetics tells us how reactants turn into products. Thermodynamics gives us the overall picture, tells us what we start with and the energy of those things, and then tells us what we end with and the energy of those things. Kinetics tells us the steps in between. Considering the difference in thermodynamics and kinetics as the difference between looking at the overall change in energy from products to reactants and looking at the changes in energy within a reaction, we can actually visualize the difference between thermodynamics and kinetics in an energy diagram. So let's do that. So we could do this with either an exothermic or an endothermic process. I'm going to do it on here for an endothermic process first. An endothermic process means what? Correct. Overall, more energy is consumed than is released. There is more energy that has to be added to the reaction to break down the bonds in the reactants than energy is released when you make the product bonds. So we see the overall amount of energy in the system increases. So we can mark on here the delta H value, which is a thermodynamic variable. Delta H tells us the difference in energy from where we start, so from those reactants, up to the products. And so the difference right here, this would be our delta H value. Kinetics, on the other hand, isn't just analyzing the difference between the very beginning, over here, the reactants, and the very end, the products. Kinetics is looking at this entire journey. So the part on this graph that kinetics is most concerned with is how much energy it takes to go from the very beginning up to the highest energetic point. And we call that amount the activation energy. So let's mark it on here. The activation energy goes from, I'm going to move over to this side so it doesn't get in the way of delta H. Activation energy is the energy required to go from the reactants, all the way up to the highest point. So this right here is our activation energy, and you'll often see it abbreviated like this with a capital E and a subscript A, that is an A. So delta H is the difference between where you start and where you end. Activation energy is the difference from where you start to your highest point. Thermodynamics doesn't care one bit about the highest energetic point. It just cares about the difference between where you start and where you end. Exothermic process. In an exothermic process, that means that more energy is released when the product bonds are formed than energy was required to break down the reactant bonds. So you can see that overall the amount of energy in the system decreases. So we would have, of course, a negative delta H. The amount of energy in the system decreases. Energy is released into the surroundings. And so in this case, again, our delta H is the difference from where we start to where we end. And again, activation energy is the amount of energy required to get from where you start to the highest energetic point. So to reiterate, kinetics is concerned with the activation energy because activation energy is part of the process in getting from the reactants to the products. Thermodynamics is not at all concerned with activation energy. It's concerned with only the difference between where you start and where you end. This unit, we're going to dig deep into the process involved in getting from the reactants to the products, not just comparing the reactants to the products, figuring out the steps in between the reactants and products, and analyzing how quickly those will be able to happen. Third level, thermodynamics tells us whether something will happen or not. And kinetics tells us the speed or the process of that happening. Let me give you an example. Diamonds and graphite. Both are carbon. They're specifically different allotropes of carbon. That piece of vocab isn't super crucial for the AP test. All it means is different elements in different states. So both are just a bunch of carbon atoms bonded together. As these two things, diamonds and graphite, are both allotropes of carbon, it's possible for one to turn into the other. And the chemical reaction, as I've sort of pictured it here as diamonds being the reactants and graphite being the products, that specific process has a negative delta G. Now, does that mean it's thermodynamically favorable or unfavorable? Correct! It is thermodynamically favorable for diamonds to turn into graphite. Now, you don't see any jewelers or people with diamonds freaking out about the ultimately unavoidable consequence of diamonds turning into graphite. No one is concerned with this, even though the delta G tells us this process is thermodynamically favorable. This process happens naturally. The reason why no one on Earth is concerned about this happening is because it happens extremely slowly. In our lifetimes, in 5 generations from now lifetimes, no diamond will have turned into graphite. This process takes such an incredibly long time that even though it is thermodynamically favorable, it does not happen at an appreciable rate.